Now let's define invertible linear transformations. So if we have two vector spaces V and W, and we have two linear transformations, T and S, where uh, one goes from V to W, and the other one goes from W to V, so going in opposite directions, right? If the composition of S and T is the identity transformation, and also the composition of T with S is the identity transformation, then we call S and T inverse transformations. T would be the inverse of S, S would be the inverse of T. The idea here is they undo each other, right? If we have S of, some vector W, we plug it in, we get some vector out here. And then if we apply T, it just takes us back to where we started. It undoes whatever transformation S did. Okay? And vice versa. S undoes whatever transformation T did. So if you imagine putting on your sock maybe as one transformation, the inverse transformation would be taking off your sock. So one undoes what the other does. Okay? In this case, a matrix that has an inverse is said to be invertible. All right, so let's look at a concrete example here. I have two linear transformations, S and T, both map R2 to R2. Here they are defined. I want to show these transformations are inverses. Okay, now according to the definition, that means that the composition S with T and T with S both need to be the identity transformation. They need to take, in both cases, they need to take us back to what we plugged in, what the original input is. Okay, so I need to check both ways. So first, I'm going to check S compose T of XY. Okay, these are inverses. Then this should give me vector XY back. Okay, let's check. So this is S of T of XY. So I'm going to start by plugging in my vector into transformation T. That's going to give me 3y 1/2 x. Okay, now I need to take transformation S, and you apply transformation S to this vector, 3y 1/2 x. So in order to do that, 3y is now the first component that I'm plugging in. It's going to take the spot of x in this relationship here. And 1/2 x is going to take the spot of y. Okay. So I'm going to plug my first component into the x. I get 1/3 x down here, but I'm plugging in 3y, so 1/3 times 3y. And then I have 1/2 x, that's my second component that I plug in. So I'll get 2 times that second component up at the top. 2 times 1/2 x. And we can see 2 times 1/2 x, that's definitely just x. 1/3 times 3y, that's definitely just y. So we started with vector xy, we ended with vector xy. That means S undid whatever T did. T did something to the vector, right? Took it to 3y 1/2 x. S just undid that operation. It inverted it. Okay? Now, it's not enough for it to just work one way. So we've checked S compose T. That's the identity transformation. We also need to check T compose F. Sometimes it's possible for it to work one way, but not the other. So you got to be careful here. Okay. So we've checked S composed T. Now let's check T composed S. Okay, so if I take S of xy, I get 2y 1/3 x. And if I plug that into T, I plug 2y in for x. That's going to be 1/2 times 2y. in the second component of the result. And I'm plugging 1/3 x in for the y in this expression. So I'm going to have a 3y in the first component of the result vector. So that becomes 3 times 1/3 x. And 3 times 1/3 is 1. 1/2 times 2 is 1. So I get xy again. And so S compose T is the identity transformation. T compose S is the identity transformation, which means these are inverse transformations. We might write S is equal to T inverse and T is equal to S inverse. Okay? Here, note the inverse notation is meant for functional inverse. That's a little different from a multiplicative inverse, like when we have a matrix inverse. Okay? The idea is similar, though. It undoes whatever the first operation did. Okay? Now, it turns out that if T is an invertible linear transformation, and S is the inverse of T, then S is also linear. So the inverse of a linear transformation is also a linear transformation. Let's prove this. Okay? So let's start by choosing W1. So actually, first, let me write it this way. Observe S is going to map W to V, right? If S is an inverse of T, then it has to undo whatever T does. Since T takes V to W, S better move it back from W to V. Okay? So S maps W to V. So what I want to show is that S is linear, so that means it preserves linear combinations. We saw that that is an equivalent condition. Okay? So let's let W1 and W2 be vectors in W. I don't really care which ones. And A1 and A2 be scalars. Set V1 equal to S of W1 and V2 equal to S of W2. Note, because T and S are inverses, that T of V1 is going to be equal to W1 and T of V2 is going to be equal to W2. Okay, and so the reasoning for this last line here, we take one of these and just apply transformation T to both sides. Okay, well, T of S of W2, T and S are inverses, right? So if I apply T to S, I should just get back what I started with, which was W2. All right, which is exactly this statement here. All right, so that's all I'm doing. I'm just expressing the relationship in a different way between V1 and W1, between V2 and W2. All right? Now observe, what we're going to do is we're going to take a linear combination of vectors W1 and W2. Now, if I could show that this linear combination is preserved over the transformation, then that is equivalent to our two conditions for a linear transformation. That is, that it preserves scalar multiplication and that it preserves vector addition. These are the usual conditions we need to prove that a transformation is linear, right? If I could show this is true, if I could show this is true, then this is a linear transformation. What I'm doing is I'm just kind of doing it all at once. I have a sum of vectors, and those vectors also have scalar multiples. Okay, so I'm just throwing it all together all at once. If I can show both these properties hold with this, then I will have what I want. Okay. So what I'm going to do here is I'm going to plug in what I know W1 and W2 to be, namely T of V1 and T of V2. So I get S of A1, and instead of W1, I'm going to write T of V1 plus A2 T of V2. All right, but T is a linear transformation. So inside the parentheses, I have scalar multiplication, I have vector addition. I can move all those operations inside transformation T. So I get transformation of A1 V1 plus A2 V2. Okay? Just use the fact that T is a linear transformation, which we know. We're told T is a linear transformation. We're trying to show that S is. Now, S and T are inverses. So what one does, the other undoes. Whatever T does to this set of vectors, S is going to undo it. So in a sense, these two are going to cancel. And we just get the inside A1 V1 plus A2 V2. But what were V1 and V2 again? Another way to write V1 is S of W1. Another way to write V2 is S of W2. Okay, and actually, we're done. Okay, and now if we want to write an extra sentence, we could say, thus S is a linear transformation, which is what we were trying to prove, that the inverse of T, which was S, is a linear transformation. But why? Because it preserves the linear combination. Okay, I was able to pull out the scalar multiples. I was able to take the addition and move it outside the transformation S. All right, here the plus is on the inside, here it's on the outside, and I'm applying the transformation only to vector W1 and W2. Okay, because I can do those two things, S is a linear transformation. The only thing I assumed about S is that it is an inverse of a linear transformation T, and from that I showed that S is also a linear transformation. So any inverse of a linear transformation is also a linear transformation.